speaker, right? All right. Anybody else coming? All right. Good afternoon, everyone. Today's speaker is Daniel Castillo. Castillo, right? Castillo. Sorry to improve my I think Spanish a little bit. But and I just want to thank Daniel first of all accepting our last-minute invitation. We had a different plan for this week, but unfortunately sometimes our visitors may not be able to make it on time. So Daniel really jumped on and then accepted our invitation in the last minute. And I hope that I was thinking that he can really give us a presentation later on. Stay here, but
yeah, me too.
But I believe he will really make a great contribution to this kind of seminar series. He graduated from Universidad de los Andes, University in Bogota. That's the place that I know in Colombia. And 2016, and now he's a visiting scholar with in our research group at ATRL. His talk today is about computational modeling of the heterogeneity of asphalt mixes applicated at the macro and non-micro scales. I'm sure you will enjoy his talk, and let's just give him a round warm of applause and then get his presentation started.
I can close the door, right? So.
Yeah, let me close the door, don't worry. And then whoever wants to come can use the other door. Yeah.
Okay, well, good afternoon, everyone. Thank you, Professor Oser, for the introduction. In my last presentation, I gave you a short introduction on the work that I have been doing in the past few years. Because of that, today I wanted to share a little bit more on the actual applications that we have been developing. And of course, well, our topic is the modeling, computational modeling of heterogeneity of asphalt mixtures in both the macro and the micro scales. So the presentation today is going to be divided into 4 parts. I will start with a short introduction, then I will move on with the macro models, so the random fields and 3 applications. Then the micro scale models, so the random microstructure, and also 3 applications. And I will finish with a conclusion. So to begin, well, we know that hot mix asphalt is a heterogeneous material that results as the mixture of aggregates and asphalts and, of course, air voids when the material is compacted. We say that this is a heterogeneous material because the phases that compose it all have a very different response to environmental and mechanical loads. There are several studies in the literature, of course, in 2 dimensions and 3 dimensions that try to approach computationally the process of modeling this material. These efforts are very effective in modeling the exact configurations of aggregates, usually at a high computational cost and mostly for just one specimen, be it 2-dimensional or 3-dimensional. I want to make a comment here about the air voids, one of the phases that compose the material. This is we are seeing the internal structure of air voids of a core of asphalt material. And as we can see, air voids create a very complex internal structure inside the material. This is of high importance to us because we were always interested in the air voids as a natural way for moisture and air to access and affect the material. Several researchers have in the past reported air void contents in depth for several field cores obtained from pavements elsewhere. We wanted to study these trends because we always observe that the higher values of air voids are usually appearing on the surface. We wanted to try and replicate this kind of behavior in all of the stages of our modeling. So that is what I am showing you these results here. I will start now with the macro approximations. Here we are trying to capture the heterogeneity of the material without microstructural features. So just a quick reminder, we needed a tool that was able to capture the heterogeneity when modeling a macro scale. For the macro approximation, we are using random fields. A random field is a vector of random values which are correlated in space, such as this field that we see to the left. To the right, we see a matrix of random numbers. It is very different, of course, if we extract or try to visualize a profile of values from the random values. We're going to get a very tortuous behavior. On the contrary, if we try to do the same process to the random field, we will get a very smooth profile, because in the random field, there is an underlying correlation structure. For our macro approximation, our assumption is that all of the realizations of a random field, we are considering them to be airvoid contents inside the asphalt layer. That is why airvoids were very important to us. All of these realizations are instances of the random process. So they all share the same parameters. They all have the same average value. They all have the same standard deviation and the same correlation structure. When we take the random field to be a probable configuration of airvoids, we can follow with, let's say, procedures that we would apply over an asphalt layer, for example, extracting cores. The cores here would be columns of values. And these columns of values here, we are seeing the airvoid content in depth for several computational field cores. They resemble those fields, those results obtained from reality. But also, we can go on and visualize quantities that may be more difficult to obtain in reality, for instance, a horizontal profile. So if we get all of the top values from a layer, we could get a line like this one, the blue one, to the right, which is, in average, higher than, let's say, the red line near the bottom. All of these values are laying around an average value, which is the average value of the random field. But of course, around this value, we can see a level of variation. Another useful application for the random fields is to target different airvoid contents. For instance, these are 100 fields obtained from random fields. We target airvoids for air%, relatively low. We can do the same procedure for an average value or for a higher value. And all of the fields, all of the profiles are going to be different. They are all going to be random. But we have a degree of control over the average trend that we want to have in our computational cores. This is a concept that has become very important for us when working with random fields. Suppose these are all the realizations or instances of a random field. We can select a location that is the same location for all of the fields, and all of these values we can find, for example, the average of them, right? This is a process that we can calculate for all of the locations inside the random field. If we do that, we get an average field, which is actually the average of all of these values in all of the locations. But most important, we can perform the same procedure with the standard deviation of all of these values. The result would be a field that is showing us the uncertainty of this variable everywhere in the layer. This is possible because the geometry of all of the fields is the same. We are usually focusing our attention more on this kind of results, the standard deviation. So with this in mind, I will present you the first methodology for modeling heterogeneity at the macro scale. We start with the process of construction of the layer. This is just one of the geometries that we use, but of course we can use any size that we want. And we are saying that the airvoid content everywhere in the layer can be represented by an instance of a random field. To go on and perform a mechanical analysis, we need to correlate these values of air voids with information that is that we can use to perform a mechanical analysis, such as linear viscoelastic properties, for example. To do this, we are relying on reported data on the literature, and we are correlating every value of air voids in the field with a set of values of linear viscoelastic properties. So this is a field that we can input into finite elements, and we can apply a load, and we can extract a response, a mechanical response. This procedure can be performed any number of times for all of the instances, the different instances of our random fields. One of the first applications that we found for the random fields was trying to correlate their behavior with the quality of compaction. So suppose a contractor is building and compacting some layers. If they perform a very consistent job, a very good job, we would expect the field, if we extract some field cores from those layers, we would expect the variability among these fields to be relatively low. So these are 10 field cores obtained from 10 random fields. They are computational, and they exhibit low variability among the average values. So we are linking this to a good quality of compaction. And in the same sense, if that dispersion increases, we can get, or we say, that those layers had a poor quality of compaction. And we can see this, because if this is a layer that was that had good quality of compaction. We can see that the air voids are evenly and smoothly distributed, and so are the corresponding linear viscoelastic properties. But if we start with a layer to the right that was poorly compacted, there are going to be areas with very low air void contents, with very high air void contents, and these areas are going to reflect on the linear viscoelastic properties, creating areas with very high and very low values of, let's say, instantaneous modulus, and we do not want that level of heterogeneity. If we take several layers and that were with good level of compaction, and we subject them to an applied load, for instance, this figure is showing us 2 wheels over a layer. This is the strain of a strip of elements below the wheel. If the layers had good compaction quality, we can see that the profiles, while they are varying because the fields are all different, they exhibit a low level of variability. But if we start with layers that were poorly compacted, we can get a result such as this one to the right, where the average value may be similar, but the poor quality of compaction is resulting in a very uncertain response of the strain. This dispersion, we can calculate it in this location, right? Because this is the location where the maximum horizontal strain appears. But we can do that calculation everywhere in the layer to create fields of uncertainty of the strain. These are the fields of uncertainty for layers that were with good quality of compaction and layers with poor quality of compaction. And what we see is that when the quality of compaction is poor, the uncertainty in the behavior of the resulting strain is higher everywhere, including the areas where the maximum horizontal strain appears. This can also be visualized in a, oops. Oh, well, okay. I removed that slide, sorry. Okay. For our next application, we wanted to compare the random field methodology with a simpler approach to modeling heterogeneity. A simpler approach, for example, would be instead of having heterogeneous layers, we could have homogeneous layers. In a homogeneous layer, such as this one, this to the left, the air void content is the same everywhere inside the layer. That is why the layers have only one color. We wanted to subject a set of 1,000 of these layers and 1,000 of these layers to the same mechanical load to see how different the results would be. And what we got was something similar in the sense that while the average value, even it was a little bit lower for the random fields, the average value of strain, we did get a highly increased dispersion of the strain for the cases with random fields. These extreme values of strain appear on the layers because the random fields may have higher values or lower values than their average. This is very important for us because it is a way of calculating or estimating probable results that are not going to be or are not expected if we are using a different or simpler approach. This, on top of the figure, we have the average fields for both cases. The fields are very similar because they show the average strain for the homogeneous case and for the random field case. We wanted these fields to be similar, actually, because we wanted both approaches to be comparable. But if we compare the standard deviation of the strain, we get this result. Here we can see that the uncertainty in the strain is higher everywhere in the layer for the random fields approach. Close to the area where the maximum horizontal strain appears, it can be 8 times higher than that of the homogeneous case. And if we extract all of these maximum horizontal strains, we can calculate the probability density function of this quantity. We can compare the probability density function of that maximum strain for the homogeneous and the random field case. The average value may be similar, but if we observe this high tail to the end of the random field's probability density function, we can see all of the maximum strains that may appear and that may reflect even in life cycle to fatigue that are never expected in the homogeneous case. We followed a similar procedure to couple the mechanical effects with environmental effects, temperature diffusion and moisture diffusion. For temperature, we correlated air void content with coefficients of thermal diffusion. So when we had a coefficient of thermal diffusion, a field of coefficients inside our asphalt layer, we were able to apply a temperature profile on top of the structure. This is a temperature measured during one day. During that day, we can select 2 moments in time. In one of the moments, the temperature is low, and in the other, the temperature is high. We can extract the field of temperatures at both moments in time, and together with the information of temperature and the air void values, we can calculate the actual set of linear viscoelastic properties that will describe the behavior of the material at that time of the day. Then we can apply, well, the mechanical load. We perform this analysis for layers with good compaction quality and poor compaction quality. When the compaction quality was good, we found that the uncertainty in the strain was similar for both the cases loaded early in the morning and in the afternoon. But when the compaction quality was poor, we found a high increase in dispersion when the temperature was high. So not only the poor compaction quality is negatively affecting the uncertainty of the strain, but also the combined effect of poor compaction quality and high temperatures. This is a summary of the maximum horizontal strains that we extracted from the analysis. The cases that we call the warm cases loaded in the afternoon, of course, they all exhibited higher horizontal strain. But as the compaction quality gets poorer, we can also see the strains increasing its dispersion. It is loading. We followed a similar methodology for the coupling with moisture. In this time, we had fields of coefficients of moisture diffusion. And the profiles that we applied on the layer, in this case on top of the layer and on the bottom of the layer, represent the variations of moisture during one day and the recharge of moisture coming from the natural soil. we let moisture to diffuse during 6 months, and at the end of every month, we applied a mechanical load. The fields of linear viscoelastic properties this time were calculated depending on the actual relative humidity at the moment of loading and the initial air void contents. On the last presentation, I showed you these results. This is the diffusion of moisture entering one of the layers in an uneven fashion. But not only we can do this for one of the layers, we can also select one location inside of our layers, for instance, this point here below one of the wheels. And we can observe the diffusion of moisture through that point for all of the different layers. This is what this figure is showing us. So we can see that in some of the layers, the air void conditions around that point made easy is the process of moisture diffusion. So we can see that moisture can enter very fast for some of the layers. For other layers, the contrary was true, and moisture took a longer time to enter. In general, we observed a high level of dispersion, or the highest level of dispersion, around day number 40. To the left, we are seeing the profiles of strain below one of the wheels. The green curves correspond to the dry layers after they were constructed, and the blue curves correspond to the layers 6 months after construction. We can see, and not only see, but measure the increase in average horizontal strain. And of course, this increase happens because the material is detrimentally affected by the moisture. To the right, we can see a summary of the horizontal strain, the maximum horizontal strain, every month for all of the layers. We can see that it is increasing with time, increasing with the intake of moisture, but we were also interested in calculating the dispersion of these values, and we found that the dispersion does not increase in time. So those were a few of the applications of our macro approximations to modeling heterogeneity. Now we continue with the micro approximations. Remember that for our macro approximations, random fields were a tool that was able to capture heterogeneity. For the micro approximations, we also needed a tool, and we decided to create something that we call MG for short, or microstructure generator, which is able to create random configurations of aggregates and air voids. The process to create one of these microstructures starts with creating a set of aggregates, much like these, then creating a set of air voids, such as what we see on the right, and then putting them all together and locating them inside a geometric domain. Once again, we were carefully controlling the locations of the air voids so that they would follow a predefined random trend, because we were always interested in the environmental effects and the diffusion of moisture and temperature inside of the specimens. Here we are observing a full gradation of aggregates. Of course, we can see that they are following some kind of size distribution. We do this by creating shapes and assigning to the shape a characteristic length that we call the seep size. This is what is marked with these small dots on the upper part of the figure. The seep size is telling us the size of the smaller sieve through which the particle could pass. So this information, together with the gradation and some volumetric considerations, we can take them all into account to create and to comply to any gradation that we want. The process of random fields had instances because it was a random process. The MG has also instances, and all of these instances are the result of running the random field with the same input parameters. If we run it once, we can get one microstructure. If we run it again with the same parameters, we will get a microstructure that is different in the location of aggregates and air voids, but that will share all of the input parameters that we want. For instance, these three realizations all share the same aggregate area, the same air void area, the same number of aggregates, and their aggregates comply to the same gradation. And of course, the shape of the specimen is the same. So these are what we call replicates, much or very similar to what one could expect from replicates in the laboratory. So with our MG in order, this is the methodology that we proposed for the micro approximations to heterogeneity. We start with one or several, we usually use hundreds of microstructures of aggregates and air voids. Then we proceed to model them in finite elements. For this stage, we are applying, we need to select a constitutive behavior for both aggregates and the mastic phase. For the mastic, we are using a nonlinear viscoelastic viscodamage constitutive behavior developed by researchers at Texas A&M University. With all of this information together, we can subject these specimens to mechanical load and extract information such as displacement or reaction force or damage everywhere inside the specimens. I think it is. Okay. So I will present you now the methodology for our first application of the micro approach to heterogeneity. We selected two gradations, one with nominal maximum aggregate size of 12.5 millimeters and the other with 19 millimeters. And for each gradation, we selected three air void contents, low, average, and high, 4, 7, and 10%. Each of these combinations gives us one case. One case is composed of 100 microstructures with the same gradation and air void content. And we subjected all of these specimens to a controlled tensile stress condition. One of the results that we can get, of course, is the displacement on the rigid plate that is on top of the specimen. If we observe just one of the figures, we are seeing the displacement in time for all of the specimens in one case. So all of these specimens had the same gradation and the same air void content. But of course, the presence of aggregates and air voids in different locations is inducing a level of dispersion in the response. We can get an average value, but we can also calculate a dispersion in the final displacement, for instance, at the end of the test. We can also compare the three figures on the upper part of the slide are the displacement curves for all of the cases with the gradation 12.5 millimeters. When we had more air voids, we were getting more displacement in average. So that is why the curves to the right are higher. And also, if we observe the two figures to the right, those two cases had the same air void content but different gradation. And once again, the change in one of the parameters, in this case the gradation, induced an average displacement at the end of the test that was different. In this case, this gradation performed a little better. Taking some time. Okay. This is a detail of the damage that appears inside two specimens. To the left, this is a specimen or a detail of a specimen with low air void content. And to the right, this is a detail of a specimen with high air void content. We observed that when we have lower air void contents, there are less interruptions in the matrix phase. And thus, the damage that appears gets more evenly dispersed and usually gets to lower values than when we have more air voids, because we have more interruptions in the matrix phase. And we see damage concentrating around very specific points, usually between aggregates. The nonlinear viscoelastic viscodamage constitutive behavior that we use, that is called PANDA, has this variable, damage density, which is 0 for an element that is not damaged and 1 for a fully damaged element. So we also wanted to study the development of damage inside of the specimen. So what we did was, for one specimen, we established a threshold of 0.9. So every time an element inside the specimen surpassed that value of damage, we accumulated its area. So for one specimen, we will get a curve of average, or a curve of damaged area in time. What we are seeing here are all of the curves of damage or damage evolution inside the specimens, inside all of them, in the same location as in the previous slide. So the three figures on the upper part correspond to the 12.5 millimeter gradation. And once again, we observe that the presence of airvoids, in average, more airvoids induced more damage accumulated at the end. And also, a difference in gradation induced a difference in the final accumulated damage, which was, in average, lower for the 20.5 millimeter gradation. So this is a tool that is enabling some kind of comparison between two specific gradations, for instance. Well, before I show you this, the black curve everywhere in the figures is the average damage evolution for each case. If we take the slope of this curve, we would be calculating the rate of damage for every case. So this is the rate of damage for the gradation 12.5 millimeters, and every curve corresponds to one airvoid content. When we had more airvoids, the damage ratio was higher. But what I think it is most interesting is that for the second gradation, we didn't get a behavior that was, let's say, so even for increase in airvoids. For instance, in this case, the cases with 10% airvoids, the damage ratio stopped increasing at around 200 seconds into the test. So what this is showing us is that the methodology is able to find these kind of particularities in the behavior of a specific gradation, any gradation that we want. For our second approach, we activated the moisture damage model in PANDA. So now we were able to study the detrimental effect of moisture inside the specimens. We selected two airvoid contents, low and high, 4% and 10%. And for every geometry, we had two finite element models. One in which the diffusivity of aggregates and the mastic was low, so it was difficult for moisture to enter. And the other had the same geometry, but it had high diffusivity. We performed we created 100 specimens for low diffusivity and high diffusivity, and we subjected them to these conditions: moisture diffusion from the edges during 1 year, and during that year we applied this displacement 3 times. The reason for having low diffusivity and high diffusivity is that even when the values of diffusivity, for instance, of the mastic phase are reported in the laboratory, these values exhibit a very high variability. So we selected 2 extremes from the literature. Remember that for every specimen, we obtain a different and unique response, in this case, of force and stress. I'm sorry, this is that is the next slide. Here we have the moisture diffusion in the low diffusivity cases. We can see that for any 2 geometries, it was very difficult for moisture to get in, because at the end of the year, at most 10% of the moisture that was applied on the edges had reached barely, it had barely moved from the edges. On the contrary, for the high diffusivity cases, at the end of the test, the lowest value of moisture that we could find was around 0.95 of that of the edges. So this is the kind of extreme behavior that we wanted to induce. This is the reaction that we are getting, the force that we are getting for all of the specimens. For the low diffusivity cases to the left and the stress-strain response, and for the high diffusivity cases to the right and the stress-strain response. Once again, less airvoids created the induced less damage in the sample because it was more difficult for moisture to get in and damage. And we can see that the stress-strain cycles start reaching lower values also because of the moisture damage. This is information that we can show not only in average form but also in dispersion everywhere in time. For our final application, we wanted to study the effect of morphological properties of the aggregates on the mechanical response of the microstructures. These kinds of properties are usually characterized using three properties: form, angularity, and texture. But texture is usually measured through images. So we decided to stay with form and angularity for now. Very briefly, the angularity of a shape or an aggregate is calculated using, well, these are just two equations that are used to calculate angularity and form. Angularity is calculated as an accumulation of changes in the direction of the edge. So when we get an edge like this one, we can get a shape that doesn't look like an aggregate anymore, but has a very high angularity. And if we have a low angularity, we can get shapes such as this one. The form index is calculated in a very similar way, but not with direction, but with distance from the center to the edge of the form. So when the form index is very low, we get shapes similar to circles, and shapes that have this shape when the form index is very high. We had a number of parameters inside of the MG that are responsible for creating the shapes of the aggregates. What we did was we performed a very careful calibration of these parameters so that we were able to target any value of AI, angularity index, or any value of form index. It turns out that it is not trivial, for instance, to keep one constant value of AI while increasing the values of Fi. I mean, it is not as easy as modifying one parameter. These two measurements are very correlated, and it is somehow difficult to try and separate them. At the end, what we were able to do was to select one value, fixed value of angularity. In this case, all of these structures have angularity 0.07. And while keeping that average value inside the sample, we can increase the form. The aggregates here are color-coded according to their value of form, which can go from 0.78 here to as much as 4.48 here. And we proposed 5 cases. These are only 3 with these characteristics. And also, we selected one fixed value of form index. In this case, was 3. And while keeping that average value form, we increased angularity. So the average angularity of all of these samples is increasing. This is a summary of the cases that we proposed. So each point represents one sample. And if we see, for example, all of the samples in case 1, these are microstructures which have in average 0.07 angularity and around 1.25 form index. And as the form index increases, and we can see that in these shapes, we try to keep the angularity as close to 0.07 as possible. And we perform the same procedure with a fixed value form, increasing angularity. And we subjected all of these samples, I think 1,000 in total, to a very simple mechanical load. These are the results, and these are specific results for this process that I mentioned to you, that is keeping one of these variables constant while the other moves. So at constant angularity, when the form index increased, we found that in average, the modulus, or at least the slope of the stress-strain curve, decreased, and also did the damage that accumulated at the end of the test. And the opposite was true for the fixed Fi values. When we increased angularity, keeping the same value of form index, we observed that the modulus increased, and so did the damage at the end of the test. So I just wanted to summarize that after the work that we performed, we believe that these methodologies were effective in trying to capture heterogeneity, both at the macro and micro scale. That process of capturing heterogeneity was and is our objective during our work. We also believe that the methodologies were effective in reproducing random configurations of aggregates and aeroboids that were valid. Those were the microstructures that we were using for all of the analysis. And also, regarding the coupling with environmental effects, during the course of our work, we calculated and presented several measurements of average and uncertainty values related with the effect of environmental processes on the asphalt layers. So all of the work that I presented to you today, except for this one, the last part, is still submitted. But the rest of the work, we have presented it, and it is published in papers that you can read when you want. And I just want to finish by acknowledging the work of Dr. Silvia Caro, my advisor in Colombia, because all of this work, we performed it together. And also Dr. Iyaz Masad, my co-advisor during my PhD. So that is all. Thank you.
All right. Questions?
I do have a question. Thank you for the presentation. My question is, how do you assume the interface between the aggregate and the binder when you were doing the micromechanical modeling?
Okay. I think Anjali asked something similar. I understand that the interface and some of the models that are found in the literature have a lot of work trying to study exactly how to model that interface. The thing about these models is that we don't have only one realization, but several. And the kinds of elements, for instance, cohesive zone elements, or the kinds of techniques that would be needed to model a very accurate interface would add a lot of computational cost to all of our methodologies. So right now, all of the microstructures that you are seeing just have a partition in the same geometry. And some sections of the partition are assigned the properties of the aggregates. Some sections are assigned the properties of the airboids. But there is no special consideration on the interfaces right now.
But do you think that would affect the results somehow?
Probably. What we expect when we add an element to our model is that sometimes the trends that we find, for instance, when going from low airboid content to high airboid content, the trends may still apply. Probably percentual changes will also still apply. Maybe the actual values that will be predicted will be different. That may be the case. Professor.
The last part of your work was really interesting. Overall, I think your work is really interesting, Daniel. I really
Thank you.
I like your presentation. It's very nice, and to use this computational really techniques to understand asphalt's mixtures behavior better. I think that's really an area that is a lot of research needed. But in the last part, when you study the aggregate morphology, how do you decide those aggregates are, being compacted in the volume that you assign to them? Because based on their morphology, they may not really reach to the same state of density.
Density.
Yes.
Okay. We have several criteria to guarantee comparability among our cases. All of the specimens that you are seeing have the same aggregate area. that was one big assumption. Because if you notice, there are more particles here than there. And that effect, I think we are observing that effect on the results. But the thing is, we believe that we needed to establish some criteria to be fixed in order for the cases to be comparable. Once we decided that a target value of 65% of the area was going to be covered by aggregates, the number of aggregates following a given gradation was, well, not automatically, but it was fixed also. So yes, I understand, for instance, in that figure to the right, what you say is that maybe all of those aggregates may not be really, it may not be physically possible to compact them in that configuration. I understand. I understand. That is a consideration that I have actually not think about.
Your work is really nice right after the compaction finishes.
Yeah.
There's a lot more needed during the compaction stage. That's what really affects at the end of the day the performance. All the heterogeneity that you're showing in the first part of your presentation is all about the mixture itself, but also the compaction process. So you take it from there after it's compacted, and then you assume some random field. But I think there was also some work in Ayat Massad's group, I think, to simulate the compaction as well, right? I mean,
yes,
yeah.
yes.
Using similar techniques.
Yes, you're right, Professor.
And one more question. Do you have any physics governing your random fields? Like in the microscale applications, you assume some distribution of airways, or is there any criteria or constraint you apply to your models that you received from the field observations?
What we did was, let me show you. One of the analyses that can be performed not only on this kind of results, but actually in any result, is to take one of these curves and separate it into two curves. One of those curves will have the general trend, and if you subtract that general trend from any of these, you would get a random trend centered around 0. Right? So what we are saying is each of these curves is the result of a random process centered around 0 plus some trend. So that is what we do. The trends, we created some of these trends randomly, but they are not randomly in the sense that they can start from a higher value and reach a lower value, but they always have the average target that we want. And to that smooth trend, we add the random field, which is the random part of the trend. So that the trends that we get to the end look very similar to this. The fields look very similar to this. But it was needed to divide the random fields into these two kinds of parts, because if we didn't do that, we would get a field, for example, this field is not modified. So you don't get higher values near the surface. You get higher values somewhere.
That's one observation that you use
Mm-hmm.
to affect or constrain to affect your distribution of airways.
Yes.
Surface has the higher airways.
Yeah.
That's why I think that's affected normal. How about the mixture dependency? Because some mixtures may have much higher, variation in their airway distribution. Some mixtures can be really tight.
Okay.
Are there any like feedback that you have not done but planning to incorporate into your models?
Well, we actually let me show you. Maybe here in the compaction.
And the layer, the thickness of the compaction, many things can affect it.
Yes. Yes. I mean, when we were performing our work, we noticed that there are several variables, of course, in the process of construction and compaction, that if you go to the field, you are always going to find variation. You are going to find variation in the applied load. You are going to find variation in the thickness of the layers. All of these variables were, we could have modeled them. We could have added variability on them. But then we will have many levels of variability, and we wanted to isolate the variability of one of those sources. we selected airboids because this source was distributed everywhere in the layer. But of course, we could also add variability to the thickness, or we could add variability to the load applied. And the final results will have to be, reanalyzed to try and separate the influence of the variability, the new variability that we included, and from the variability of the airboids. Or we could remove them also. Regarding the compaction, for instance, the curves to the right. While we are increasing the dispersion between cores, we also have the possibility of keeping the dispersion for each core to be not that high. So what you mentioned about some mixtures having more dispersion and less dispersion, I would say that is a parameter of the field. We can select how dispersed we want the field to be. So if we needed experimental measurements of the dispersion of some material, and it was higher than a given material, we increase the dispersion that we want, and the fields are going to behave accordingly. That is what will happen.
Anybody else? We can wrap up. Maybe one last question, Daniel. So where do you want this entire things to be applied at the end of the day? How do you see the future of this method being applied in payment design applications?
Okay. Probably I wanted to show this correlation we did with the compaction quality, because this is one of the objectives that I think would be reachable using this technique. I think from the macro approach, this will be one of the most important results. Not only with airboids, but it could also be applied to any other variables, such as percent asphalt or something inside the layer. From the micro approach, I think the possibilities go more into the reach of different laboratory tests, because of all of the tests, for instance, they have different geometries. For instance, the SCB geometry, which is a semicircle, or I have seen some of these full circles with the holes. The possibility of the MG to create and to adapt to any geometry, and to take that geometry and in a very short time generating thousands of specimens following the same geometry. I think that will be one of the most powerful aspects to seek for its appliance in practice, I think.
There's not any other questions. Let's just thank Daniel one more time.